Hello everyone, we're getting into now chapter 4 in calculus, antiderivatives and indefinite integration. This chapter talks about really the second major component of calculus besides derivatives, what are called the antiderivatives, which we will generally end up referring to as integration. So let's go ahead and get started. So we've spent many months on finding derivatives from an original function, but what about the ability to go the other way? So what if we wanted to find a function whose derivative is 3x squared? We would use our knowledge of derivatives and probably conclude that, okay, so to get a derivative of 3x squared, we gotta use an x cubed. Okay, and recognize that the power will come down in front and subtract 1. Now, so that means x cubed is an antiderivative of f because its derivative is 3x squared. Now, the reason we say an antiderivative and not the is because there's a lot of different functions whose derivative is 3x squared. So our general definition of an antiderivative is that a function f is an antiderivative of f on an interval I when f prime of x equals f of x for all x and I. They're just basically saying it's as long as their derivative is 3x squared over the whole domain, it's fine. Now, if you look down below though, x cubed minus 5, and x cubed plus 97, for example, all have the same derivative because when you take the derivative of a constant, it becomes 0. Which is why we only refer to something as an antiderivative and not the antiderivative. So all of these functions generally will have something in common. They have an x cubed, but then they have potentially a constant. So technically speaking, if we want to capture all of the antiderivatives, we need x cubed plus c to be the antiderivative of f because we don't know what kind of constant was in there when we took the derivative because it would have essentially killed any constant when you take the derivative. So as a general theorem for representing our antiderivatives, if f is an antiderivative of little f on an interval I, and g is an antiderivative of f on the interval I, if and only if g is of the form f of x plus c, where all x and I, where c is a constant. Basically, they're saying if you have multiple antiderivatives of a function f, they can only differ by a constant value added or subtracted. Now, the way that we will deal with this is that when we're trying to find the antiderivatives of a function, for example, of 3x squared, we will say it's x cubed plus c because we don't really know what constant was there. And this constant, generally, we call it the constant of integration because anytime you integrate or take an antiderivative, it will produce this plus c in virtually every scenario as long as there's no known input values and the integral is indefinite, which means it goes from over the whole domain. There's something we'll learn about later called definite integrals where the plus c doesn't come into play. The family of functions represented by g, that x cubed plus c, is called the general antiderivative with a general solution. If we needed a specific solution, we would have to have some kind of piece of information in order to determine what that constant is. Now, most of the time when you're taking the integral, you are usually in differential form. Remember that instead of dy over dx, sometimes you may just have y prime equals 3x, but also we talked about differential form was that the dx is moved over to the other side where dy equals 2 dx. Suppose you wanted to find the general solution of the differential equation dy dx equals 2. It's a fancy way of saying the slope of the line is 2. Now we know plenty of lines can have the slope 2. It would be y equals 2x plus something. But all we really need to do for this is to find a function whose derivative is 2, like 2x, and use theorem 4.1 to conclude that the general solution will be 2x plus c, where c is some constant. And these are just a bunch of different lines with different plus c's that generally represent what your function could look like whose derivative is 2. And again, as I mentioned earlier, when you have dy dx equals f of x, it's convenient to move the dx to the other side. The reason for that is when you're integrating, you would like to know what variable you're taking the integral of, or what you're taking the antiderivative of. And when you're doing that, you'll notice this little curly Q looking sign. This represents the integral of f of x with respect to x. So what the dx tells you is what variable you're taking the integral of. And the way that's read is that you're finding the antiderivative or integral of f with respect to x. So again, the dx is there to help you identify what variable you're taking the integral with respect to. And if you continue on in calculus further, you'll find that you can have multivariable calculus, which is really calculus 3. And so you might be integrating over different variables, but more importantly, sometimes you'll have problems that are with respect to time, so you would like to integrate with respect to time, in which case your function will likely be with respect to time as well, and it wouldn't be good to have a whole bunch of equations with t in them and then a dx afterwards, so it should usually match. Now, one thing to note is the derivative and the antiderivative, or differentiation and integration, are inverse operations. So if you have some derivative and you take the integral of it, you go back to the original function plus c. Similarly, if you take an integral of a function, then the derivative of the function, you get exactly back to the function itself. So there's a slight nuance there in that the derivative of the integral is the original function, but the integral of the derivative is the original function plus or minus c, to generally indicate that they are inverses-ish. They're mostly inverses, I guess is what I would say. Not necessarily specifically inverses. Now, with that, there's going to come rules about these inverses and how they work. But not all of our rules for derivatives are going to have the same inverse rule to go with them. So our basic integration rules are the derivative of a constant was 0. That means the integral of 0 is a constant, goes backwards. The derivative of a number times x was just the number, the x went away. The integral of number gives you a number times x plus a constant, because there could be a 0 attached to it, generally speaking, or any other constant. But the idea here is because the integral of 0 is a constant, technically k is k plus 0, so that constant would still come into play. You can kind of think of it like that. Okay, the derivative of number, like a scalar, times a function was just that scalar times the derivative. Similarly, you can integrate a function when it has a multiple in front of it. Similarly, adding and subtracting as well. But take note specifically of the power rule more than anything else. The derivative power rule wise was you brought the power down and you subtracted one from the power. So when you're integrating something x to a power, you're instead going to add 1 to the power and divide by that new power to undo kind of the derivative action. And of course, there's still a plus c. One thing to note is that n should not be -1. Because you can't divide by 0. There's something special will happen for those kind of equations. Similarly, in addition to those basic rules for the derivatives of the trig functions, the integrals just kind of go backwards, but they also have that plus c. So that's one thing to keep in mind when you're doing this. And in the next video, we'll do some examples and some problems that are associated with kind of the basic antiderivatives or integrals of functions.